Okay, today we're going to move forward with some new types of additional components on Arduino. You recently got a good look at this, which is just a GPS antenna receiver. And it's kind of a gateway to what we're going to talk about next, in that it is its own circuit. It's its own contained sort of what we might call component, but it's a singular component. Today what we're going to do is introduce breakout boards. Now, breakout boards come in all kinds of shapes and sizes, and for the purposes of today's lesson, we're going to start with this. It's called the MPL 3115 altitude pressure and temperature sensor. It's from SparkFun. And when we say breakout board, what we mean is this is a board that has a pin socket that plugs into a breadboard or like a solderable breadboard. And what's broken out is its own circuit. So let me show you some other examples here of some breakout boards. So that one measures temperature, altitude, and pressure. This is what's called an IMU, or inertial measurement unit. This is in all of your phones. It's the thing that helps the phone read tilt in up to 6 axes. This is a 3-axis, so this reads tilt on an X, Y, and Z. And also acceleration. So this is sometimes referred to as an accelerometer, but it's its own little circuit, and it takes all of its own internal circuitry and runs them out to pins that you can plug into a breadboard. This is a motor driver. If you're ever running stepper motors, this is called the Big Easy stepper driver. And it basically just simplifies the circuitry that's necessary to go from Arduino logic, and I'm going to come back to that word in just a second, and to turn it into sort of instructions for how to move specifically a stepper motor. This is an air quality sensor. You can see it's got its own little chip in there, and then it's got, these are just little resistors and capacitors that help it talk through this row of pins to an Arduino via a breadboard. This is an electret microphone. So this is just for sound input. If you've got a sound-based project, this is something that can measure decibels and then talk again to Arduino. And this is like a pretty cool, sophisticated breakout board that's just an LCD display. And so sometimes we want a mobile screen available to read the types of info that we're getting in and out of Arduino. These are all types of breakout boards. So I'm going to come back to the word logic here for a second, because that's relevant to this sensor. So this sensor, when you look up the data sheet, it runs on 3.3 volt rather than 5 volt. And you'll see that when we hook up the breadboard here. We're going to power it through 3.3 volt. And then it's talking through this system called I2C. And I'm not going to over-explain that right now, but I2C is Arduino's onboard system that uses serial data and a serial clock. And the clock is to synchronize the timing between this and the logic of the Arduino. And the data is literally that. It's just the data coming in from this piece and going into the Arduino. And serial data with I2C either uses a 5 volt or a 3.3 volt logic. There is what's called a logic level shifter board, and then there's a really simple way to just reduce 5 volt down to 3.3 volt with some resistors, which we're going to use today. This is just a 330 ohm resistor, and this is all in the hookup guide for the MPL 3115 altitude pressure sensor. The example code as well is available on the SparkFun page. I'm just going to look at it really quickly and point out one key component of the code. This first line is include, and then in brackets it says wire.h. So this is a library that needs to be called on in the code. And wire is one that's built into Arduino. Now, this one, the include SparkFun MPL 3115A2.h, is a library that you need to have added to Arduino, and you can do that through, let's see, I believe it's Tools, maybe it's Edit. Is it Edit? Where is it? Where is my library? There it is. So Include Library. If you don't have it, you go to Manage Libraries. A screen should pop up for your all available libraries, and in this case you would type something like MPL and give it a moment to update. Let's see, MPL 3115, and when it updates, here we go. So that's the Adafruit library. That is maybe a slightly different circuit, so we're looking for right here, and you can see I've already got it installed. If it's not installed already, this install button will be active. So you need to add this to your code before it will work. Going back down into the code, we're doing a couple of other hopefully familiar things. One, we've just created a variable called myPressure, which is the instance of that object. We need wire to begin. That's starting the I2C or the SCL-SDA, the clock and data pins on your Arduino, which let me bounce over here and see if we can spot clock and data. So that's serial clock and serial data up in the top corner there. So back to the code. MyPressure begin is this. These are variables that are specific to the sensor, and that sensor has a code library, which, check this out, because this was written by the founder and excellent documentarian. Here are the available functions that are just part of that, again, MPL 3115 library. So when we write that include MPL 3115.h, what becomes available to us are all of these functions. And there's a little description of each of those functions. And this basic code uses some of those functions. This is the configuration, some of the variables from that library. It's setting the mode of the altimeter, an oversample rate, and enable event flags. I'm going to be honest with you, without reading up on that, I'm not sure what that stuff does. If we look down in the loop, we're looking at a variable called altitude, a variable called pressure, and a variable called temperature. Should be pretty self-explanatory. And what they do is use the myPressure and then dot read pressure as a function. So it's saying myPressure is the name of my sensor, and it's saying dot read pressure, and that's then parentheses and a semicolon. That is giving this float variable pressure a value. And then it's saying serial print line this pressure, so on and so forth. It does that all the way through to temperature and pressure and altitude. And altitude is a derivative of pressure. We can talk more about that later. It's a little technical. And then serial.println just makes the code print one line of each of these values and then go down to the next line. And we'll take a look at that in a second, but let's start with putting our circuit together. I'm going to take my sensor, place it right about here. I want to give myself plenty of room on that side to make some connections. I'm going to look closely at my clock, which is the third pin, and I'm going to jump that over to here across the divide in the breadboard with a 330 ohm resistor that's where is it? It's orange, brown, autofocus. You'll see that. That's in your SparkFun pack of resistor fun. And then another one for the serial data. I'm just going to put them right next to each other. For starters, obviously I need to power the circuit, and I'm going to use the rails on the side of the breadboard to keep things a little cleaner visually. Now, careful on this. Looking at the power, we've got 5 volt and we've got 3.3 volt. As I said with this breakout board, we need to power it with 3.3. So make sure you get it in the right pin there. Okay, so now my power rail's got 3.3 power and 5 volt power. I'm going to jump from my ground rail over to my ground pin here. All right. And I'm going to jump from my 3.3 volt over to my VCC or voltage pin here. Okay, just 2 more wires. If you look closely at the breakout board, you'll see I've connected these resistors to the data and clock line, and I'm just going to jump data to data and clock to clock over here on the Arduino side with a couple of wire colors that make sense to me. That's data and that's clock. And if you guys see these little loop-to-loops in my jumper wire, it's just to shorten it so it's not in the way of the camera so much. It doesn't really change that much. So, okay, everything's connected. I'm going to jump over to the code side and upload. And I should see some RXTX lights flashing here momentarily. Flashy, flashy. Very simple. Right? That's all there is to it. And if we've got everything connected right, now when I go over to my serial monitor, I'm going to see altitude, pressure, and temperature reading from this sensor. Let's watch altitude. This is the altitude sitting on the desk, and I'm at about 5088, 5089 feet, which sounds a little low for Boulder, but maybe I'm just sad today. But I'm gonna physically raise this up, and let's watch the altitude. So yeah, pretty sensitive. Like I raised it up 3 feet, and it's reading between 3 and 6 feet. So this is not a really expensive like altitude sensor. It is, you know, this is not a super high-end thing like you'd want to put in an aerospace project per se. This is an inexpensive way to measure altitude, pressure, and temperature. And right now it is a balmy 76.44 degrees Fahrenheit here at Building 61. So that's it. Really simple circuit. All it involves is making use of a pre-built circuit that's on its own board that we call a breakout board. Okay, so now we have our first breakout board sensor here, but let's imagine we want to power this thing not via a laptop. We know that the code's working, we know that the sensor data is coming through the Arduino via the clock and data pins, I2C, and we know that that data is being transmitted to the serial monitor through the serial port through our transmit, oh, let me get this out of there, I kind of cheated, through our TX, RX pins. So we know when we're uploading code, we see TX and RX blink every time the Arduino and the laptop are transmitting and receiving little packets of information between each other. What's also happening is if you look down here on pins 0 and 1, you see another TX, RX, and that is also, it's the same data, transmit, receive. This is transmitting that data to, in the case that we just watched, the serial monitor. What we can do is also take that transmitted data and record it separately. So if we sent this thing out into the field and we wanted to log our data, we could record it to a micro SD card. And there is a breakout board called OpenLog, which is just a little micro SD card socket. And of course, again, with all of the necessary pins to connect them to the Arduino, but not necessarily to the serial monitor. So let's take this data through the serial port and actually write it onto this card. Card should go into the breakout board first, and it just has that little click lock. I'm going to put it pretty close to my sensor. As with all things, we want to connect power and ground first. So I'm going to go from my breadboard ground to my OpenLog card reader ground. Come on, come on. Oh, geez. Dealing with tiny wires. There it goes. Okay. Ground. Ground to ground. Power to power. And you might see some lights blinking on the card reader. Now, do not follow SparkFun's written directions for this. I'm sorry, this is one that they just completely overcomplicated. The only thing you need to do is jump a wire from transmit on the Arduino, or TX, which is pin 1, boom, to RX, or receive data, on the OpenLog. And look at that little blue light right there. That little blue light is exactly what we're looking for. Those are packets of data coming in to the card reader. We're just going to let that populate. It's coming in every second or so. And now if I'm going to disconnect my card, it's no longer reading. And I'm going to pull that out. Put this in my card reader on my laptop and open up that card in my Finder. And look, I've got logs, data logs that start counting at 0 and 1. 1 is the most recent. And there you see, like, we have a couple hundred lines, oh, not quite 100 lines of that same data that we saw on the serial monitor, but that is reading off of this micro SD card. So that is a good way to set up a remote data logging station with a micro SD card. Super simple, power and ground, TX here to RX here. All right, I'm going to show you how to connect a basic GPS receiver component. This is the little GPS receiver. It doesn't look like much, does it? But imagine that one of these is essentially in your phone, and the component is certainly not that big. You can see this is, it sort of has its own circuitry. Everything that's needed to make this device work is sort of internal here, and it's just a 3-lead wire. Power and ground are red and black respectively, and then the signal out is a white wire. This one's really simple. This is utilizing some basic code, which we'll look at here in a second. I'm going to go ahead and power it up to 5 volt and ground on the Arduino side. And then the signal's going into pin 4. And let's look at why by taking a look at the code. So if I scroll down here from the top, I've brought in my tiny GPS++ library, the .h file. And I brought in this interesting piece of code here that you haven't seen before. It's called software serial. So software serial is a really useful tool. It allows you to basically move your transmit and receive pins to separate pins. And that's in case, like we're going to see in the near future, you're using your built-in transmit and receive pins to do something like log data. It's setting up a baud rate that is sort of similar to what you see here, 9600 baud. And there's that code already working. And what it does is say that I want to set my receive pin to pin 4 and my transmit pin to pin 3, and that happens in this line of code right here. So really all it's doing is adding an extra line for serial communication that we will sort of use the GPS antenna receiver to talk to, and then include that in our data recording, which we'll look at here in a little bit. So I'm going to upload the code, and we'll see, of course, our usual transmit and receive flashing lights. And takes just a sec. And now let's go back to the serial monitor. We're going to see something not super exciting here because we are under a roof. And so I'm going to turn off auto scroll so we can read this a little bit easier. You can see right here we're getting invalid. And that only means one simple thing. Because we're inside, the receiver is not picking up a GPS satellite. It actually needs to hit probably 3 separate satellites to lock in its location. But I'm indoors, and the satellites can't see through the building, at least not yet. And so my serial readout is reading invalid. I have not connected to a literal satellite flying around in space. But I assure you, if you take this outside, whether it be with your laptop or you'll see how to make that even more portable in the near future, then this device will pick up satellites in outer space. All right, now we have seen the breakout board, in this case the altitude, pressure, temperature sensor, and logging onto the OpenLog SD card reader board. Now I want to circle back to the GPS antenna, and we're just going to add this into the mix. So we'll be using simultaneously software serial and our sort of serial read-write that's built in to the Arduino. Circuit is really simple, same wiring diagram as just the GPS by itself. It is using 5 volt. I'm going to connect my ground first and then power into 5 volt. And my software serial is on pin 4. This is getting quite messy here. So same wiring diagram as just the GPS by itself. I'm going to plug transmit back to receive for the OpenLog. And I don't have, let's see, sometimes we got to make sure that the OpenLog is actually reading. There it is. Blue flashy light. I'm going to go over to Arduino. So this is a combination code, and I'm going to try and let you guys hack this together. I'm going to speed through this really quickly so that it's blurry and you can't see it. It's called Flight Tracker. It's Flight Tracker for humans, and I'll explain the difference coming up here. We just want to talk to computers in a slightly different way than we do humans when we're processing this data or moving on to data visualization. So my code's already uploaded actually. So I just want to open my serial monitor and take a look at what we're getting here. I'm going to stop the auto scroll because it's difficult to see on the screen. We are getting, this is the GPS data. It says invalid and it's not registering a date time because I am inside, I'm under a roof. I've got no clear line of sight to a GPS satellite flying around Earth. But when I'm standing outside with this code, I will get, as you have seen, just using the GPS, my date, time, and coordinates. And I'm still getting my altitude, pressure, and temperature, which is very similar, as you see, to what we got with just that sensor. And so this is the combination circuit. Essentially, this is the black box of a flight tracker. We've got GPS, we've got altitude, pressure, and temperature, and we're writing to an SD card. And just to reinforce this, as far as being able to move this data, I'm gonna take the micro SD, pop it back into my laptop, and go to my Finder there. There's my latest data log, and you can see now I've got code that's, once I'm in line of sight of a GPS tower, going to give me location, altitude, pressure, and temperature on an SD card. So there it is. That is your flight tracker combined circuit. And let's look a little bit into how to shrink this down into something a little lighter weight so it will go up. Okay, I want to introduce a handy little item that can help reduce the size or weight of a circuit board. Once we've breadboarded something, we might want to kind of tidy up the package a little bit. Or in the case of a high altitude balloon, you know, every gram counts. So reducing the weight of that large breadboard down to something like this can be really useful. So this is a solderable breadboard. This is one from SparkFun. Similarly to a sort of plug-in breadboard, a solderless breadboard, it is electrically connected in the short rows here. So I can set up, for instance, like a power and ground rail here, and then run power and ground to my whole circuit. Soldering itself, of course, is a skill that you want to practice, but there's a couple of things to, you know, take advantage of in this situation. One is we've got header pins in our sensors or our breakout boards, and that pin spacing is the same in the solderable breadboard. So we could, for instance, solder this directly into the board just by hitting those 5 pins there. But keep in mind, components can and will break or burn out or just need to be replaced. And so another way to sort of set these up is to sort of pretend like this is a small Arduino. We've got, you know, these sort of female header pins in here, and we can plug male header pins into them. And we have, of course, component level male header pins and female header pins as well. And we can cut these to sort of any number. And let's just try that and plug in one of our sensors as an example of the advantages of a solderable breadboard. Let's see, let's do this with the MPL sensor. So I've got 1, 2, 3, 4, 5, 6 pins, right? So I want to cut enough female headers for 6 sockets. And I'm going to count 1, 2, 3, 4, 5, 6. Get this out of here. It's messing with the focus. I'm going to count 6, and I'm going to take my normal wire cutter, and I'm going to cut right on top of number 7. So 1, 2, 3, 4, 5, 6. I'm going to line that up, you can see there, with the 7th pin right on top of it, and just crunch. Okay. So that breaks that off, and it cuts out the 7th pin right there. And I've got a fairly tidy 6-pin socket. Because I am a crafts person and I care, I'm gonna trim back some of that little plastic edge on the end. Bring back in my helping hands. And I will have spent a lot of time figuring out where on this board I want to place all my components. But this is more of a demo. I think I can get away with just that number of spaces left over. Now this gets tricky. I'm using helping hands to help the video appear useful. And you can see there's the tiny little pins that you're going to solder on the bottom side. What I'm going to do is do the first one down on the table to let the table just hold that header in there. And I'll show you a quick trick. Oh, I forgot my solder, 1 second. So I'll solder my first pin right here. Make sure the tip of my soldering iron is shiny and clean. I get a tiny little bit of solder on that tip. I place it on that pin, and there's a little pad around that pin. Let's see how close we can get it. You can see it right here. I want the solder to really cover that entire pad so that I know I've got a good strong connection, and I've also got a good electrical connection. Now, if I look at this from this angle, it's not very straight, and I don't like that. But while I've only got one pin soldered, I'm gonna melt that pin on the back side, and with my other finger, I'm just gonna straighten up that header and hold it until it cools. Now, that's a little cleaner, a little more vertical. Go back to the helping hands so that you can see things a little better here on the camera. Awesome. And I'm just gonna hit the next 5 pins in order, moving towards me. 1, 2, 3, 4, and 5. Taking great care to make sure I have not made a solder bridge between any of those pins, because that, of course, will, at worst, it could short circuit and burn out my components. At best, it might just confuse the information flowing from my breakout board back to my Arduino. But now that I've got that handy little socket, now I can just plug my component in there. Rad. And of course, on the rest of the board, I would connect my grounds, connect my wires. In the case of the logic level shift that needs to go from 3.3 volt here back to the clock and data pins, I would solder in my resistors in there, my 330 ohm resistors, and so on and so forth. Also, as a matter of habit, you wouldn't really want to start with this tall component, because now that's sort of in my way. And for that circuit, I really want some jumper wires moving across here and across here. And I would do all of the lowest components first, and then get to the taller component, and then the taller component, and the taller component, all the way up. So obviously I'm going to redesign that on paper or make notes for myself first. But this is just a quick example of how a solderable breadboard can reduce the size and weight of a breadboard circuit.